my name is Reagan, and today we're going to be doing experiment 10, ionic and covalent bonding, conductivity of solutions of ionic and covalent bonds. All bonds in chemicals are either ionic or covalent. Ionic bonds are bonds where the electrons are unshared, so that one of the atoms has more electron density than another atom. An example of this is sodium chloride. Sodium is more likely to be ionized, that is, give up an electron to chloride, and chloride is more likely to have higher electron density. Covalent bonds are where the electron density is shared between two atoms. For instance, in compounds that are the same atom, such as H2 gas, O2 gas, these have two oxygen atoms or two hydrogen atoms, and they will equally share electron density. When we put compounds in a solution, they can either ionize, that is, dissolve into water, such as table salt into water, and become ions, like a sodium ion, which is positively charged, or a chloride ion, which is negatively charged. This all depends on their electronegativity. Electronegativity is a number that defines how likely an atom is to want to absorb electron density or to give up its electron density. So for instance, chlorine is very electronegative and sodium is not electronegative. So when we have an ionic compound that we put into water and they become ionized, we call this an electrolyte. And electrolytes can carry conductivity. That is, it allows electricity to be passed through the solution. Compounds that do not form ions in solution are called non-electrolytes, such as sugar in water. These ions do not have very high conductance and therefore do not allow electricity to pass easily through water. So today we're going to be reviewing a number of solutions and measuring their conductivity using the microlab apparatus and a conductivity meter. But before we get started, we need to talk about safety. To be safe in the lab, you need to make sure you're wearing your lab coat buttoned all the way up. You need to have no bare skin below the waist. That includes long pants and closed-toed shoes. And make sure your ankles are covered by your pants. You need to be wearing gloves and also need to be wearing your safety goggles. Lastly, any loose hair needs to be tied back, so that way it doesn't get into any of the solutions that we're preparing, which may damage your hair or yourself. So to start, we need to talk about the materials and the equipment that we're going to use for this lab. We have a number of ionic solutions here and some non-ionic solutions. So for instance, we have barium hydroxide, we have sulfuric acid, we have a sucrose solution, which is table sugar in water, we have a methanol solution, we have hydrochloric acid and sodium hydroxide. We're also going to be testing the conductance of distilled water and also tap water from the tap in your lab. Lastly, we'll also be using a thionyl blue indicator that will allow us to know the equivalence point of the barium hydroxide and sulfuric acid, so that way we know when we're at a pH of 7. And to measure conductance, we're going to be using the microlab apparatus connected to a computer and a conductivity meter that we will plug into the microlab instrument. So that concludes the methods. Let's get started by testing some of these solutions first and see what their conductivity is when measured with the conductivity meter. So before we begin testing the conductivity of different solutions, we need to first set up the computer so that we can begin taking conductivity measurements using the microlab. So first, open your microlab software, and then you will want to select the first option, which is a microlab experiment in the experiment type window. When the experiment comes up, you'll want to add a sensor. And the sensor you'll want to add is the conductivity sensor. So from the drop-down menu, you can select conductivity. And then you will click the input that is inserted to on the instrument, which is the one that says conductance. So in the graphic on the computer, you'll want to select that input as well. And then select the first range and use the factory calibration. You will then see a conductivity readout in the bottom right-hand corner of the screen. This is the only thing you'll need for this lab, because we're not going to be doing any graphing with time or anything like that. So we don't need to add any more sensors. We're ready to start the experiment. So the first thing that we're going to measure is some distilled water that we got from our distilled water bottle. So we will add a little bit to an Erlenmeyer flask or any other type of beaker, just enough to cover the tip of the conductivity meter. Once you have your distilled water in a flask, then put in your conductivity meter, which will start measuring the conductance of this solution on your screen in the bottom right-hand corner. You don't necessarily need to press start, since you're just taking the conductivity reading and you're not really graphing or using data with this. So you can write down the conductance of the distilled water, then remove your probe and place it aside, and then dump out your distilled water and then get some tap water from the lab. So again, we can take our tap water and then add the conductivity meter and read the conductivity that is measured using the instrument. You will notice that the conductivity of tap water is significantly higher than distilled water. And that is because it contains a lot more ionic species in it than distilled water, where those ionic species have been removed. So now that we have measured some solutions with ionic species in them, we're going to measure a solution that has a non-electrolyte in it, which is sucrose or table sugar. So we will add some of the sucrose water to our Erlenmeyer flask. We don't need very much, just enough to cover the bottom of the electrode. And then you can add your conductivity meter to your flask and measure the conductance. The conductance will probably be lower than the deionized water that you measured earlier, and definitely lower than the tap water that you measured because it's a non-electrolytic solution. So now that you have measured the sucrose water, we will then move on to measure methanol. Methanol is a polar solvent, meaning that it does carry some charge on the methanol molecule itself. Part of the methanol molecule is more non-polar than the other side, but we will probably not see very much conductivity from this solution because electricity will not move easily through it. So we've added it to a beaker, and then we can put in our probe and measure the conductivity. Once you have finished measuring the conductivity, you can then wipe off or rinse off your conductivity meter. And then we will proceed to the next part of the experiment, where we will measure the conductivity of hydrochloric acid and sodium hydroxide, and then mix them together into solution, and then measure the conductivity of that solution. So for the next part of the experiment, we're going to be measuring some baryonic solutions, a strong base and a strong acid, and then we're going to be mixing them together and measuring their conductance after we mix them. So to begin, we're going to be using 0.1 molar sodium hydroxide, but we're going to want to dilute this 10 times into 0.01 molar sodium hydroxide. We don't need it nearly this concentrated in order to get this conductivity readings. So we'll use a graduated cylinder and first add 5 milliliters of the sodium hydroxide to the graduated cylinder. We can then add 45 milliliters of deionized water, or up until the 50 milliliter mark on the graduated cylinder. Once we have done that, we can pour it into a beaker and set it aside until later. And then using another graduated cylinder, or after you've cleaned out your previous graduated cylinder, you can do the same thing for hydrochloric acid by adding 5 milliliters of hydrochloric acid to your graduated cylinder, and then diluting the acid with water. We can then pour this solution into another beaker and then begin to measure each of their conductance. Before we measure the conductivity of our two solutions, we need to change the conductivity mode in the software to high conductivity mode from low conductivity mode, where we were before when we were measuring our distilled water and our tap water. So you'll need to remove the sensor that we added previously, and then add the sensor again, like we did before, but this time choose the high conductivity range, which is 0 to 20,000. Now we can again start measuring the conductivity of our solutions by placing the conductivity probe into solution and then observing the conductivity on the meter. After we measure the conductivity of our sodium hydroxide, we can rinse off our probe and then measure the conductivity of our hydrochloric acid. After we measure the conductivity of the hydrochloric acid, we can then mix these together by adding the sodium hydroxide to our hydrochloric acid. And then, after they have been mixed together, measure the conductivity one more time. The conductivity should have gone down significantly from your previous readings, but it will still be higher than when you had the tap water. That is because you've neutralized the hydronium and the hydroxide ions that were in solution, and these ions tend to carry charge better than sodium and chloride that are in solution. We will now move on to our sulfuric acid and barium hydroxide using our indicator. So first, we're going to measure the conductivity of these solutions by themselves. So you'll need to add some sulfuric acid to a beaker, enough to cover the bottom of the conductivity meter or probe, and then you'll want to add some barium hydroxide, about the same amount, to another beaker. So in this case, it was about 50 milliliters. We can then measure the conductivity of each of these solutions by themselves and record the readings that we get. The conductivity will be significantly higher for the acid than it was for hydrochloric acid because we didn't dilute it, and similarly for our barium hydroxide as compared to our sodium hydroxide because once again we didn't dilute these. So after we have measured the conductivity of those two solutions, we can add a couple drops of our thionyl blue indicator to the sulfuric acid, which will indicate that our sulfuric acid is indeed an acid by turning red. We can then slowly add our barium hydroxide solution to our sulfuric acid solution until the indicator changes colors, and at that point we want to stop. You can either do this dropwise or you can carefully pour it into the sulfuric acid solution. So the end point will be a bluish color. It's cloudy because the barium sulfate is forming a precipitate, which is suspended in solution. But if you overshoot the end point too much, you can just add a little bit of sulfuric acid until you reverse it to the pink color, and then try and get the end point right on when the color changes. Once we've reached the end point, we can then, once again, measure the conductivity of our solution, which once again will then significantly reduce from the solutions by themselves as we neutralize the hydronium and hydroxide ions that are present in the solution and form barium sulfate. After you measure the mixture, that concludes the lab. So please ask your TA if you need any help, or if you need help disposing the chemical or with the microlab software. I'm Reagan. I'll see you in the next video.